Hello and good evening, and welcome back. Some topics related to science and technology and nuclear technology we are talking. So today I'll be spending around 1.5 hours. Maybe I will take one more session, maybe tomorrow, depending upon what I require. But that is the tentative plan right now. So they're all mainly preliminary point of view information, which will be useful for you, and questions are asked from this nuclear technology in preliminary also. So be careful about that. Right. So disaster management, Meenakshi is asking. So we will be. I mean, we were supposed to, because of all these some expert faculty were supposed to come because of the COVID disaster. Disaster management could not take place till now. Okay. So anyway, so maybe during the main exam point of view time, now we will do some classes. We will allow, at that time we will relay for all of you. Okay. Right now, no immediate plans. It is not required for preliminary in any case. So we will see at that time. Now, in the nuclear, a couple of points. This uranium, I was talking about the nuclear technology and the application. I talked about the application in the previous class. So let me some more things like uranium deposits or uranium resource in India. I would like to discuss that. Uranium resources. See, in fact, India has very little or very less uranium resources in India. I told that, because of that reason only we went for a particular nuclear energy policy. And we were not able to import uranium during the, since we did not sign NPT till 2008. So between 1974 to 1974 to 2008, we were under the strict regulation, or other the NSG, Nuclear Supplier Group, were not allowing us to import any uranium from any country because we did not sign NPT. But by 2008, Indo-US nuclear deal, and we got an exemption from NSG. So otherwise, we have only around 37,000 tons which can be extracted, it seems, or around available, which can be extracted. And the production is around 1,060 tons production, meaning this is not the ore, the uranium ore which we are talking. Okay, that is what approximately. And whatever requirements we had, we were, even in 2013, we were importing almost 40% of our requirements. Okay, 40% of our requirements we were importing, even in 2013. So that means when we were having only around 6,800 or so megawatts of installed capacity, and if we are importing almost 40%, what we are able to generate is only around 4,000 or something, or maybe even 40. If you are 40% requirements we are importing, 40% of requirements we were importing. So that means 60% we were able to generate. So around 4,000, 4,200 megawatt electricity production we were able to do by using our indigenous uranium source. So it is quite less. Okay. And we don't have much resources, but we are generating, or we are producing, and Uranium Corporation of India is responsible for the production. Uranium Corporation of India is responsible for the production, and it is a subsidiary of Department of Atomic Energy, subsidiary of Department of Atomic Energy, and we started our production in Jaduguda and Bhatin in Jharkhand, both in Jharkhand, in 1967 itself. Then we also started production from another place in Jharkhand. All are in the East Singhbhum district. Singhbhum district, East Singhbhum district. And then we also had another mine at a place called Narwa Pahar. That was started in 1995. Year is not very important. Then Turamdi. That is in 2002. So Jaduguda, Bhatin, Narwa Pahar, then Turamdi, all in Jharkhand. Okay, these are all shaft mining, going deep inside and then mining. Okay, and all these were the ores were taken to a mill, the uranium ore mill at a place. The mill is located at Jaduguda. Okay. Then we have also, we have announced some more mines. So these were the main. Then we also, in the early 2000s, we announced in Jharkhand, one is called Bandhu Hurang. Then Bagjata. Then Mohuldi. So again, all the three in Jharkhand. Then in Meghalaya, Domia Sat, Domia Siat. And Mautaba. Okay, this is in Meghalaya, Domia Siat and Mautaba region with a mill there. And also in Andhra Pradesh, Lambapur. And then Peddagatu. In Andhra Pradesh. And both in Nalgonda district. Okay, it is in Nalgonda district. So this Bandhu Hurang is an open cut mine. All others are shaft mines. This is an open cut mine. So we have a couple of mines. So three states, Jharkhand, Meghalaya, and then of course Andhra Pradesh. Okay, so we have this, but not sufficient for our use. So these are the mines, the uranium mines of India. Earlier ones I already said, the famous ones, Jaduguda, Bhatin, Narwa Pahar, Turamdi, all are operational much before. Then we have also operated Bandhu Hurang, Bagjata, Mohuldi, then in Meghalaya, Domia Siat, and then Lambapur and Peddagatu in Nalgonda district of Andhra Pradesh. So these were the potential, and that is, but the production is quite less. It is not sufficient for our use. Even we are talking about by 2020, 20,000 megawatts of electricity from nuclear power. We would not have been managing in any case anyway. Now, after the Indo-US nuclear deal, there is a concept of strategic uranium reserve. strategic uranium reserve, this is part of Indo-US nuclear deal. In case of a disruption in the supply of uranium by US for the plant which they are committed and they are not able to do, what is the disruption? Maybe because of India conducting a test or something like that. So we agreed to have a strategic uranium reserve whereby we will have some reserve and it will not be affecting the the electricity production in these power plants, or rather it will not, we will not be stopping the electricity, what you call power plants for shortage of uranium. That is the idea behind the whole thing. So the strategic uranium reserve will be under the inspection of IAEA. International Atomic Energy Agency. And we already have contracts. I have already mentioned we have contracts with now US can supply, France, Russia, Kazakhstan, then Namibia, Mongolia, and we have even signed one for Uzbekistan also. Recently we have signed an agreement with Uzbekistan also. And even Australia, Canada, I forgot Mongolia, Australia, Canada. So these are some of the countries with which we have signed with Canada also. We have signed agreements for uranium supply. And Rawatbata, RAPS, the Rawatbata Atomic Power Station, Rawatbata 2, became the first pressurized heavy water reactor in Rawatbata in Rajasthan, in Kota. This became the first reactor to be fueled by an imported or fueled by imported uranium. Okay. Rawatbata plant, the pressurized heavy water reactors, became the first to be fueled with imported uranium. Okay. And we are, as I told you, we are predominantly importing uranium from Russia. Right now, France, of course, we were doing. Kazakhstan. Okay. So these are three countries from where substantial import is there. Mongolia, yes. Canada we have, Namibia we are even setting up plants and all, and so that is how we are planning. So this strategic reserve is an idea whereby we can store uranium such a way that even if there is a disruption in the supply of uranium in future, we will be using this reserve for our nuclear power plants. That is the idea behind the whole thing. Okay. So that is about it. And as I told you, Uzbekistan we have signed in March 2020. Please remember, only in March 2020 India signed a contract with Uzbekistan, and we are getting supply from Uzbekistan also now. Okay. So Kazakhstan, even Uzbekistan. Uzbekistan is the latest with which we are. So ultimately, we have a plan, or we are storing some uranium so that it will be used as a reserve in case of a major disruption in supply to India. We will be using this reserve for fuel as a fuel. So that is the idea behind the whole thing. Okay. So anyway, so that's about the fuel reserve. Now also let me just come to thorium. as I mentioned earlier, India has plenty of thorium, more abundant, and at least we had, at least 4 times more fuel. I mean, that's what they are saying. And the best part about the thorium is found in the beach sands of Kerala. And also, it is, but predominantly in Kerala, also in Tamil Nadu and Orissa. But most of the deposits are found in Kerala, the beach sands of Kerala. And the idea is the amount of energy contained in thorium. Some very interesting fact I would like to say, the amount of energy contained in thorium reserves. Because thorium right now we are not using anywhere, but it has huge potential is there. We can convert thorium into uranium-233. I discussed about that in the fast breeder reactors. So the amount of thorium contained in amount of energy contained in thorium reserves in the whole earth, okay, according to experts, it is more than the combined total energy that is left in petroleum, coal, other fossil fuels and uranium put together. So it is reserves in earth is more than the combined energy that is left in petroleum, coal, natural gas and even uranium. Coal plus petroleum plus natural gas plus uranium, whatever be the total energy left, more than that energy is left in thorium. That is what experts are saying. That is huge. And according to International Atomic Energy Agency, IAEA, India has the largest reserves of thorium in the world. India has the largest reserves of thorium in the world, which is approximately 6,50,000 tons. 6,50,000 tons. And according to IAEA, this is more than 25% of the total reserves of the world. More than 25% of the total reserves of the world. So India has around 6,50,000 tons, which is more than 25% of the total reserves of the world. So huge. And another advantage is thorium can generate 8 times more energy from a unit mass compared to natural uranium. So whatever energy, please note, very interesting, thorium can produce 8 times more energy per unit mass of uranium. Okay, suppose 1 kilogram of uranium and 1 kilogram of thorium, thorium can produce 8 times more energy. Okay, 8 times the amount of energy per unit mass compared to natural uranium. So thorium, I have already said thorium can be converted into uranium-233, and this U-233 is equal to 8 times energy by natural uranium. Okay, 8 times energy compared to natural uranium. So, thorium can be converted into uranium-233. I am repeating this. Thorium can be converted into uranium-233, and this 233, uranium-233, can produce 8 times more energy compared to natural uranium. So, that is something great. And the best part is, one more part is, this thorium or rather this thorium and then uranium, it produces less toxic waste. Also, it produces less toxic nuclear waste. So, that is another advantage. It produces less toxic nuclear waste also. But the issue is, we have to convert thorium into uranium-233. Fast breeder reactors are required. Fast breeder reactor construction is still going on. We have not mastered it. So, it is a slightly complex technology, because then reprocessing of the fuel is required. Then reprocessed fuel can be used as fuel in some other reactor. So, there is some complexity. Nuclear waste management is involved. Reprocessing is involved. Please do not forget, 233 we can extract by reprocessing of the fuel. I talked about this, reprocessing of spent fuel. So, there are some complexities. That is why most of the countries in the world, they are not producing electricity from thorium, they are producing from uranium, because it is easy to manage. But these potentials are there. That is the point I would like to make right now. Okay. So, that is the situation as far as thorium is concerned. We have to convert thorium into uranium-233 in a fast breeder reactor. Right now the technology, but there are other technologies being considered. Scientists are working on that. If things work out, then thorium has huge potential, because it has 8 times more energy. And also, that is why it is said, the combined energy of all fossil fuels plus uranium put together, thorium's energy is more than that. Okay. So, that is something really great. So, which we have to we can in future. So, there is a, but again, the best part is, of course, it has nuclear waste. Nuclear waste management is a problem. We have already seen that, but it is not greenhouse gas emitting. So, nuclear technologies advantages, it will not emit greenhouse gas. Okay. So, that is situation as far as this uranium, thorium deposits and resources are concerned. Now, let me move into nuclear medicine. Okay, let us talk about nuclear medicine. So, nuclear medicine, it uses radiation. See, both are harmful. I mean, when Ben Johnson is asking which one is more harmful, see, the moment radiation is there, the moment there is electromagnetic radiation, gamma ray, X-ray, if it is radiated from that, and if you are exposed to this radiation, it is harmful. There is no doubt regarding, both are harmful, but it all depends upon how much you are exposed, how much radiation it is hitting your body, that is it. If it is exposed more than a particular level, you will die, as simple as that. There is no difference, or rather there is no difference, because both will ultimately release gamma rays. Okay. So, anyway, so coming to nuclear medicine, it uses, normally there are 2-3 ways. One, it uses radiation. In medicine, if you are using nuclear technology, that is the point, radiation to provide diagnostic information. We use radiation to provide diagnostic information. especially about the functioning of specific organs like kidney or thyroid and all. Okay, so we are using nuclear radiation, or rather the radiation, the amount of the way energy is released is used for providing diagnostic, to diagnose, to identify a particular problem in an organ. Then we also use radiotherapy. We use radiotherapy to treat some of the medical conditions, especially cancer. Okay. Then we also use some of the nuclear isotopes of element, the nuclear isotopes in palliative care. Palliative care means, a person who is terminally ill, who is suffering from lot of pain, the pain, to control the pain, a nuclear, some of the isotopes are used. We will come to that. So that is the palliative. Palliative medicine means a medicine which is not to cure the disease, but to reduce the pain. If somebody is in the terminally ill, I mean, there is no chance of recovering. But at that time, if that person is is full of pain also, if we can give some medicine to reduce the pain, so that is what the concept of this palliative care. Okay, so then some of the nuclear isotopes are used in the palliative care to reduce pain. Then this nuclear radiation is also used in sterilization of medical equipments. Okay, medical equipments, especially surgical equipments, surgical ones. Before surgery, because there no no bacteria, no virus, nothing should be there. Even the microorganisms should not be there in a surgical equipment, so that it may be adding to the problem later on. So sterilization by using nuclear radiation, that is also radioisotopes are used here. So this nuclear medicine, we can say it's a branch of medicine. And in the nuclear medicine, the main activity is not radiotherapy, using radiation to provide diagnostic information or medical imaging. Okay, so medical imaging, it's a branch of medicine, and it's a branch or nuclear medicine. Nuclear medicine is a branch in medicine as well as in medical imaging, especially in medical imaging. Okay, and we use this radioactive substance, radioactive isotopes, in diagnosis and in some cases in therapy also, but mainly in diagnosis, in some cases in therapy also. So we measure the radiation emitted, and accordingly we will be getting the information. And many a times this information, or rather the imaging, the medical imaging, is using gamma cameras, okay, where gamma rays are emitted. Imaging is collected, or imaging is done by using gamma cameras. Gamma camera means a camera which can absorb, which can record gamma rays. So then in therapy, if you are using, in diagnosis we can understand, in therapy if you are using, we are nuclear, these isotopes are given either for curing or in the palliative care. That is what we are talking about that. Some of the examples, and please remember cobalt 60 and cesium 137 are the two important gamma ray sources. If you are using gamma rays for radiation and if you are using gamma rays to kill the cancerous cells, normally we are using the source either cobalt 60 or cesium 137. These are the two nuclear isotopes widely used for producing न्यूक्लियर आइसोटोप. नम्रता तुम तो क्लास पूरा नहीं कर रहे उसका मतलब. व्हाट इज न्यूक्लियर आइसोटोप अभी पूछ रही है तुम. तो न्यूक्लियर क्लास ही नहीं किया तुम. I have very clearly said those isotopes which, what is a radioactive isotope or nuclear isotope? What is the meaning of that? It is those isotopes which can break down by itself. Okay, those isotopes which can break down by itself. See, carbon 14, C14 is a radioactive isotope or a nuclear isotope of carbon. Okay, so and those isotopes which can break down by itself. Okay, and these are widely used for either therapy or, and so this is the, and cobalt 60 and cesium 137 are those isotopes which are used for producing gamma rays, okay, which can break down by itself and is the most widely used, okay, isotopes which can break down and produce gamma rays. Anyway, so some of the examples. So these two are for gamma rays. Unstable elements, yes, unstable isotopes, unstable isotopes. Then, technetium 99, some of the examples I'd like to give. TC99. It's a gamma ray free source of beta particles. Now, technetium 99 is used as a nuclear medicine to produce beta particles, and it is gamma ray free. It is free of gamma ray. No gamma rays, only beta rays, beta particles will be emitted. Technetium 99, and it is used for again imaging. In imaging purpose or in identifying, imaging the function of brain, in thyroid, in lungs, in liver, gallbladder, kidney, imaging of brain, gallbladder, kidney, skeleton, liver. So in all these, we are using for imaging purpose, for identifying, we are taking a picture using beta particles. Okay, beta particles are producing, gamma ray is not producing. So that is technetium. Then iodine 131. Again a beta emitter or radioiodine. It is also known as radioiodine, radioisotope. Again, used in treating cancer treatment, and again to when other problems in the thyroid glands, iodine 131 is used. Thyroid glands. Then thallium 201. Thallium 201 is again a radioactive isotope. Again, it is used in the diagnostic purpose and especially in coronary artery diseases. This is especially to study the blood flow. Thallium 201 is used to study the blood flow and any blockage in the arteries, coronary artery disease, thallium 201. Then gallium 67. Again, diagnostic purpose. Medical imaging. Okay, it is for medical imaging. Then fluorine 18. Okay, and it emits positrons. Okay, a series of, then also administration of pharmaceutical, like radioisotopes being given as medicine through intravenous injection. It will be given to subcutaneous, I mean below the skin injection, subcutaneous injection, all these things for in various purposes. So there are a series of applications there. Even other than that, cesium and 139 I already said, 137, okay, and cesium 137 gamma ray source for sterilization of blood. Sterilization of blood. Cobalt 60, I already said, even for external beam radiography or radiotherapy, cobalt. Beam of gamma rays. And again, cobalt 60 universally used in sterilization, all sterilization, and also cobalt 60 in brain cancer treatment. Cobalt 60 brain cancer treatment. Iodine 125 for again cancer treatment, iodine 125 for prostate and brain cancer. Even to evaluate the filtration rate of kidney. Okay, to evaluate the filtration rate of kidneys. Iodine 131 I already said in the thyroid cancer and all. Palladium is also used in cancer treatment. Phosphorus 32. Phosphorus 32 for blood cancer is a beta emitter. When excess red blood cells are there, okay, phosphorus 32, potassium 42, again to study the blood flow, the coronary blood flow. So a series of applications, hundreds of isotopes are used these days, okay, potassium 42. Blood flow. So, sodium 24 for the electrolytes within the body to studies for studies of electrolytes within the body, sodium 24. Okay. So, these are some of the applications in medicine. So, a series of application. I said for gamma ray source for radiation therapy, then for detection and also sterilization of blood, then sterilization of surgical equipments. So, series of applications we can see. As I was mentioning, cobalt 60, and it is the most widely used for gamma rays for sterilization purpose these days. Okay, it has wonderful applications. Then coming to nuclear food preservation. Nuclear food preservation. Okay, here we are trying to extend the shelf life of food, prevent sprouting, or prevent the decay of fruits, vegetables, etc. And in the process, we want to ensure that no loss of flavor, odor, texture, etc. And another thing is, the advantage is there is no flavor, texture, odor, etc. And all the attributes of the fresh food should be there. All the attributes of fresh food like, okay, for example, sprout inhibition in potatoes and onions, a major role, okay, because we lose a lot of quantity of potatoes and onions. So, sprout inhibition okay, low dose of radiation is required. Then, as I told you, delay in ripening of fruits, whether it is mangoes, banana, okay. So, it can be extended by a couple of weeks. The shelf life can be extended by a couple of weeks without getting decayed. Okay, ripening can be delayed. Then it can also, gamma ray radiation can eliminate seed weevil. That means in a small microorganisms, insects. Okay, it can eliminate, gamma rays can eliminate seed weevils It's an insect that is present, or that gets it stays deep inside the stone of the mango, within the mango. Okay, that seed weevil is an insect which can reside inside the stone of mango. Okay, and also we can use gamma radiations for disinfestation of grains. It can be used in disinfestation. So there can be multiple questions even in the main exam. Please don't forget. There can be questions on what are the peaceful applications. You can say everything. Then there can be a question, what is nuclear medicine? Give some examples of nuclear medicine. Then in food preservation, there can be question. So disinfestation of grains, removing the various what you call undesired elements in the grains. Okay, the fungus, for example. Okay, chemical disinfestation methods are there, such as fumigation. Okay, chemical disinfestation, say by fumigation. It may be requiring repeated fumigation, and even then the insect eggs cannot be removed. Even after fumigation, insect eggs may not be removed. Okay, if you are using a chemical disinfestation, repeated fumigation is required, and even then the eggs may not be removed. And they may also leave a lot of residue. If you are using chemical disinfestation and if you are using chemical fumigation, what will happen? It may leave residue also, harmful. It may leave harmful residue in the treated grains. So a low dose of radiation can ensure that these grain pests are completely killed and eliminated. A low dose of gamma rays can completely kill or sterilize the common grain pests. Common grain pests can be removed. Even the eggs deposited in the grain can be killed, and a single radiation exposure is sufficient for all for the entire disinfestation. Okay, single dose is sufficient. So we will be exposing these food grains to a low dose of gamma rays. Then it is also used in preservation of seafood. No, if nuclear food preservation is harmful to human being, then how will we use it? We cannot use it. So it is not. So that is why we are using it. Okay, it is we are exposing the food items for to kill the what you call infestation, or kill the small insects or the microorganisms, and without any harm to our human use. That is the whole idea. Then preservation of seafood. Okay, so by selective destruction of the spoilage bacteria. Okay, selective destruction of spoilage bacteria. Selective destruction of spoilage bacteria. So, especially the life of the iced fish. Fishes are what the moment it is caught, it is put in ice. So the the shelf life of iced fish, shelf life of iced fish can be extended by 2 weeks. Shelf life of iced fish can be extended by 2 weeks. Then even microbial decontamination of spices, another application. Microbial decontamination of spices. With a gamma ray radiation, the spices can be removed, insect infection completely. Spices will be removed from insect infection. And any microbial, a microorganism, it can be removed. Okay, so it will prevent even the loss of flavor components. Okay, prevent the loss of flavor components. Okay, so this can be used for spices, the curry powders after packing. Okay, so we are using gamma ray as the source of all these things. And please remember, we have various doses, and the doses are measured in kilogray. That is the unit. 1 kgy means 1. This is number of radiations per second. Okay, so that is the unit. The SI unit, System International Unit, is kilogray. The dosage is mentioned. If it is a low dose, less than 1 kilogray. Medium dose, 1 to 10 kilogray. And high dose, more than 10 kilogray. Radiation. So this is gray, GRAY, gray is measured in terms of number of radiation per second. Okay, so let us not get in the detail, it's science, but all you should know is we are classifying the dosage into low dose, medium dose, and high dose. In low dose and all, we have already seen low dose may be to prevent the sprouting, or in potatoes and onions and all. Then a medium dose may be in spices. Okay, medium dose is required in spices. High dose in fish, maybe meat, surgical instruments. Okay, low dose in potatoes and onions, fruits, etc. Okay, so these are the ways in which we are doing. And then please remember, we have we have a unit of Department of Atomic Energy called BRIT. Okay, radiation. I just forgot the full name. Let me just check that. Board of Radiation and Isotope Technology. Okay, Board of Radiation and Isotope Technology. This is responsible for setting up plants for food irradiation. Okay, and they have set up one at one plant called Poton at Lasalgaon. In Nasik district in Maharashtra. I think 10 tons per hour. It is for to Poton. The name, it has come from potatoes and onions. Okay, pot on potatoes and onions. For irradiation of potatoes and onions to prevent its sprouting. 10 tons per hour production, and here we are also using the same for irradiation of mangoes. Irradiation of mangoes. So, Board of Radiation and Isotope Technology, BRIT, they have set up this Poton, and also there is a spice irradiation plant it was set up by this BRIT at Vashi in Navi Mumbai. Spice irradiation plant. Okay. And here we can 20 tons per day. 20 tons per day. And they also, BRIT also has many other applications, but they have done this, and we are planning to set up more such plans to ensure that we can increase the shelf life. See, in India, we are losing almost 20% of all the food grains which we produce because of poor management. Okay, we lose almost 20% of our food grain production. So, that is how we are doing it. So, we have Poton and then spice irradiation plant at Vashi in Navi Mumbai. These are the two major plants which are set up. So, we are planning for more. Now, one in the food irradiation, I would like to add a couple of points. Some criticism and drawbacks.